Alright, I'm going to go over some problems from this um, overview of functions and their properties activity. Now this is really another one of those review topics really from Math 152. So I'm not going to go over every single problem from these. Like these first few are just rational expressions, so you had to understand the difference, like when you have addition, subtraction versus when you have multiplication, division. When you have addition, subtraction, those are the problems that you're going to have to get the LCD, and then you have to combine into a single fraction and then simplify if possible. Whereas with multiplication and division, which is 3 and 4, all you're really doing in those is you're just factoring and then canceling common factors. As long as you remember that division becomes multiplication, sorry, by reciprocal. So the phrase you would usually keep, change, flip. You would keep the first fraction the way it is, you would change the division to multiplication, and you would flip the second fraction. And then after that, it's just factoring and canceling. Okay? Now, oops, went a little too far. Now 5 and 6 are complex fractions, so those were kind of like combinations of the addition subtraction with the multiplication division. So those were a little bit different. So like 5, the way that I would usually tell people to do these is look at this numerator and denominator separately. So you look at this and you say there's two terms in the numerator, two terms in the denominator. So what I would say to do is, out of those four terms, find the LCD of all four of those terms. So the LCD of all four of those terms in this case would have been 2y squared. And then once you've identified the LCD, then you multiply the top of this fraction and the bottom of this fraction by that LCD. So I'd multiply the top by 2y squared, and I'd multiply the bottom by 2y squared. Now what ends up happening, of course, though, when you do this, is you got to distribute. So the 2y squared times this, 2y squared times this, 2y squared times this, 2y squared times this. And since you deliberately chose the LCD as what you were going to multiply by, now all those denominators are going to cancel. So when you multiply 2y squared by 2 over y, the y's cancel, and then you're left with 2y times 2. So then that would be 4y. Now when you multiply 1 times 2y squared, you just get 2y squared, so it's minus 2y squared. And then the denominator, when you multiply 3 over y squared by 2y squared, the y squareds cancel, you're left with 2, so 3 times 2 would be 6. And then 5 halves times 2y squared, the 2's cancel, and then you're left with 5y squared. So the denominator is just going to be 6 plus 5y squared. Now, what you might say at this point is you might say, oh, well, the numerator will factor. All right, I can take out a 2y, and then I'm left with 2 minus y. And then the denominator is, see, the problem here, though, of course, is the denominator doesn't factor. It's still just 6 plus 5y squared. And the idea here was you can only cancel common factors. So the only thing that this 6 plus 5y squared is going to cancel out with is another 6 plus 5y squared. So really here nothing cancels. So in effect you could have even left the previous result as your final answer, or you could have written it in factored form. It's always safer, though, to be honest with you, to factor on the chance that something might cancel at the end, right? But in this case, either one of those results would have been acceptable. Okay. Now 6, I'm not going to do the whole problem. I'm just going to tell you the mistake people make here is they don't understand what this negative 1 means. The first thing you would do here is you would just change those negative exponents into positive exponents. So x to the negative 1 is really 1 over x. And then x plus 2 to the negative 1 is 1 over x plus 2. And that's all over 2. And then you could simplify it from there, right? But that would be the first step that you'd have to do with that one. Okay. And again, there's an answer key of this in Canvas, so the ones that I'm not doing, you can always just check your answers. Okay, so now 7 and 8 are just rational equations, and they're kind of similar to addition and subtraction of rational expressions. What you do is you multiply both sides by the LCD. Because in doing that, again, what will happen is the denominators will cancel. So like in the one in number 7, the LCD would have been 12t. So you multiply both sides here by 12t, and then all the denominators are going to cancel. Right? In the one on the right, the LCD is actually x times x minus 2, because there's no common factors there. So you multiply both sides by x times x minus 2. But just on a little side note, what the mistake people make in a problem like 8 is they say, oh, look, I have an x and an x minus 2, so they have an x in common. They have an x in common, but it's really a common term. It's not a common factor. X minus 2 cannot be factored any further than that, so what you have to do is you have to think of x minus 2 as one of the factors. Right? So the LCD is just one factor, which is x, times the other factor, which is x minus 2. All right. Now 9 to 14, I'm going to do a couple of these because this is one of the topics that people have a little bit of trouble with. These would be quadratic and rational inequalities. And you don't really solve these just like a traditional inequality. What you really have to do with these is you have to set them equal to 0, factor, and then use a sign diagram. All right, that's the key here. So like the first one, x squared is greater than or equal to 9. I mean, is there a way to just kind of think about that and get it without doing a sign diagram? Yeah, if you think about like, well, when is a number squared going to be greater than or equal to 9, stuff like that. But really the safe way to do it, like if you want to do it, algebraically basically, you would set it equal to 0 first. So you'd subtract 9, so you'd have x squared minus 9 is greater than or equal to 0. And then you just factor this, and this is the difference of squares, so it factors into x minus 3 times x plus 3, and that's greater than or equal to 0. And now you just do the sign diagram. So the idea here is realize, all right, well, I have two factors, x plus 3 and x minus 3. So what are going to make those factors 0? Well, the x minus 3 is going to make that 0, and x plus 3, negative 3 is going to make that 0. And here, since the sign is greater than or equal to, I know those values are actually going to be included because those are the values that make it equal to 0. So those are actually part of my solution, so I'm going to give those closed circles. Right? So those are going to be closed circles. And now the idea of the sign diagram is you test the point in each of those three intervals there. So the next number over here would be negative 4, right? The next integer. In between negative 3 and 3, you have 0, so I can use 0 in that interval. And then the next integer to the right of 3 would be 4. So what I'm going to do now is I'm going to test all these values. So when I plug in negative 4 into there for x, what do you get? You get a negative 7 to be exact times a negative 1 to be exact. So in other words, you get a negative times a negative over here, right? You have a negative times another negative. So when you multiply two negatives, that's going to be a positive. So is a positive number something that's greater than or equal to 0? Of course it is, right? A positive number has to be greater than or equal to 0. So this interval over here is included, right? That's part of your solution. Now in the middle, when you plug in 0 into this factored form here, you get a negative 3 times a positive 3. So specifically, a negative, well, in general, I'm sorry, a negative times a positive. Right? And a negative times a positive would be a negative. So is a negative going to be greater than or equal to 0? No, right? It wouldn't be greater than or equal to 0. It would be less than. So in the middle, I'm not going to shade. All right? And then I do the same thing with the right-hand interval. All right, when I plug in 4, I get a positive 1, which I'm just going to write as a positive, times a positive 7, which again I'm going to write as a positive. So a positive times a positive is again going to be a positive. And is a positive number greater than or equal to 0? Sure. So this is also part of my solution. So what I have now is I have two intervals, the left-hand one and the right-hand one, that both make that inequality true. So that's my solution. So the left-hand interval in this case would be from negative infinity to negative 3. And since I'm including the negative 3, it gets a bracket, and then take that in union with this right-hand one, which goes from 3 included up to infinity. So my solution for this one is actually negative infinity, negative 3, union 3 infinity. Right? So all of these are going to follow that same kind of pattern. You're just going to, factor, set it equal to 0, factor, identify the zeros, and then just uh, test the intervals. Okay, so let me just do also, I guess, 13 maybe, because this is rational, so this is going to be a little bit different. So you might look at 13 and you might say, all right, well, 1 is less than x squared over x plus 6. Can I just guess and check on this? No, you can't. You got to do the same thing that we've been doing. You got to set it equal to 0. So you'd subtract 1 from both sides here. But the idea is when you subtract 1 now, you got to get a common denominator on the right side. So this is going to be 0 is less than x squared over x plus 6 minus 1. But again, think about what 1 would be if you wrote it as with a denominator of x plus 6, right? 1 is really anything over itself. So specifically, if the denominator is x plus 6 and I'm subtracting 1, I'm really subtracting x plus 6 over x plus 6. So this really here becomes x squared minus the quantity x plus 6 over x plus 6. All right, so now I distribute that negative sign, so this is really 0 is less than x squared minus x minus 6 over x plus 6. And now, of course, this should factor, right? I'm not going to give you these if they don't factor. So I now have 0 is less than, so x plus 6 is still in the denominator. And now the numerator, well, what multiplies to negative 6 and adds to negative 1? It's really going to be a negative 3 and a positive 2, right? So now this is the slight difference with rational inequalities. I also have to consider values that will make the denominator 0, right? Because when the denominator is 0, it's going to be undefined. So I not only take my zeros of the numerator here, which are 3 and negative 2, I also take the 0 of the denominator, which is negative 6. So in this case, I would do a sign diagram again, lay out the sign diagram, and now I have 3 important points, right? I've got a negative 2, a negative 6, and a positive 3. So negative 6 would be over here, negative 2 would be here, and then 3 would be here, right? And since this is just 0 is less than this fraction, or the fraction is greater than 0, those values there, the negative 6, the negative 2, and the 3, they're not going to be included, so I get open circles. All right, and then again, you do the same thing, right? And then, since I don't have a lot of space here, I'm just going to do it quickly. Like, let's say I plug in negative 7 here. When I plug in negative 7, what would happen to this fraction here? It would be a negative times a negative times a negative. So that's 3 negatives. So over there, it's going to be negative. And in the middle, let's say I plugged in negative 3, I would have a negative, and a positive, which is going to be positive, right? Now, between negative 2 and 3, I can choose 0. So when I plug in 0, I'm going to have a negative times a positive, which is going to be negative. And then in the right-hand interval there, I can choose 4, and I have a positive, which is going to be positive. But this is where you got to be careful now. You want this fraction, x minus 3 times x plus 2 over x plus 6, to be greater than 0. So you want it to be positive, in other words, right? So the negative 1 does not work. The positive 1 works. So that interval there, that negative 1 does not work. But then this last positive 1 on the right, that works. So in this instance, you actually have 2 intervals that work. And what would they be? They would be the second one, right, which is negative 6 to negative 2. And then this right-hand one, which is 3 to infinity. Okay, so that would be your solution there to that rational inequality. Negative 6, negative 2, union 3, infinity. All right, so the idea is set it equal to 0, get it as a single fraction, factor, identify the zeros, and then do your sign diagram. Now continuing with this overview of functions and their properties activity, number 15, I mean, we're going to do a lot more with transformations when we get into exponential and logarithmic functions, so I'm not really going to even worry about that at this point here. So we'll get into that later on. And I do have a whole video on composition of functions, so I'm not going to get into composition of functions either, because there's a whole video on Fogg and Goff. All right. And then, I mean, the power functions, you can really just look at what those graphs look like and their domain and range and behavior. We've already looked at some things like that when we've done polynomials. All right. Now, the one thing I do want to do is this, though, where they ask you to find a power function and a linear function that go through these 2 points, 181 and 327, and then they give you a second problem that's the same thing, just different points. So I guess start with the easier one, which is linear, right? You know the form of a linear function, right? The normal form, I guess you would call it, would just be y equals mx plus b, or you could use the point slope form, which is just y equals m times x minus x1 plus y1, either one of those. I mean, point slope is easier, and point slope is what you're going to end up using probably more frequently when you get into calculus. So I guess we'll use point slope here. So really, with point slope, the only thing you need to find is the slope, and then you're basically done, because you already have 2 points, right? 181 and 327. So all you do for the linear one is you just say, all right, well, I know my slope is going to be y2 minus y1, which is going to be 27 minus 81, over x2 minus x1, which is going to be 3 minus 1. So 27 minus 81 is really negative 54 over 3 minus 1, which is 2. So the slope in this case is just going to be negative 27. So that's your slope. And like I say, now you're really done. Now you can just write your point slope equation. Right? Your point slope equation then would just be y equals m, which is negative 27, times x minus x1. And like as you probably remember, you can use either one of these points, right? The first one or the second one. So if I use the first one, it's x minus the x1, which is 1. So it's x minus 1 plus y1, which in this case is just 81, right? Or, of course, you could have written it as y equals negative 27 times x minus 3 plus 27. So either one of those equations would be acceptable, along with the slope-intercept equation. You could have also written that, which I guess would have been y equals negative 27x plus 108, right? So any of those three would have been acceptable. Now for the power function, you got to remember the general form for the power function would have been y equals kx to the p, right? Where p is the power and k is just some other constant. Now the problem with this is, again, there's 2 unknowns, but we can't necessarily do it by as simple a method as we did with the linear, because we don't know, there's no slope of this, right? Power functions don't have slopes, so there's no formula for that. So the only thing we can do is plug in our 2 points, right, for x and y, so we can get 2 equations here. The first one would be, well, y is 81, and k is the unknown, and x is 1. So you have 81 equals k times 1 to the p. Now the nice thing about this one is I'm given the point 181, and when I plug in 1 for x, I have 1 to a power. And 1 to a power is always going to be 1. So really what I've done here, just by writing this equation, is I already have learned that 81 equals my k value. right? My k value is 81. So I'm essentially halfway there just by plugging in that one point. Okay, so I have k equals 81, and now how would I find p? I would just use the other point, right? So I would plug in my 327. So I have 27 for y. K I already know now is 81. X is 3, and I'm trying to find the power. So if I have 27 equals 81 times 3 to the p, I would divide both sides by 81, and I would actually get 1/3 equals 3 to the p, right? Because 27 divided by 81 would be 1/3. So now, I mean, technically we don't have logarithms yet because we technically are going to learn those in the second unit. But if you just remember ideas about powers here, you don't even need logarithms. 3 to what power is going to give you 1/3, right? Do you remember when you took the reciprocal? When would you do the reciprocal? If the power was actually a negative. So in this case, if p was -1, 3 to the -1 equals 1/3. So I know that p really, in this case, equals -1. So there's my two unknowns, right? And now that I have k and p, I can write my power function, right? My power function would just be f of x equals 81 times x to the -1. And that would be your power function, right? K was 81 and p was -1. Now what I realized when I just wrote that is they told me to call the power function f of x and the linear function h of x. So technically this over here should have actually been h of x. Not a big deal, but technically that's what it should have been, right? So those really should have been h of x. All right. So that was the first one. And the second one, the linear is easy again, so I'm not even going to go through the linear one. The trickier one is going to be the power function in this case, because look what happens. I know again I have y equals kx to the p. And now in this case though, the problem is I don't have a 1 comma something. I have 8, 128, and 2, 2. So let me try 2, 2 first and see what that does for me, right? If I plug in 2, 2, I'm going to have the fact that 2 equals k times 2 to the p. But the problem is I don't know what 2 to the p is. It's going to vary, right? If p is 1, it's 2. If p is 2, it's 4, so on and so forth. So I'm stuck there. So that's my first equation. 2 equals k times 2 to the p. But now I would just do the same thing with the other point, right? 128 is y. And I know x is 8. So I have 128 equals k times 8 to the p. And now some people get nervous here and they say, well, I have two equations with two different unknowns, so how can I solve this, right? They're not linear equations, so I'm not going to do like my elimination or anything like that. But actually, in effect, you are kind of doing elimination here, because what you do is you don't add these up. You can't add these two equations up. It's not going to help you. But if you actually divide them, if you do a ratio where you write equation 1, right? If I call this equation, well, call that equation 1, I guess. I can do the ratio of equation 2 to equation 1. So in other words, I'm going to write this. Equation 2 over equation 1. Right? So what is equation 2? It's 128 equals k times 8 to the p. And what's equation 1? It's 2 equals k times 2 to the p. And now I just write this as a ratio. So it looks like this. And now, similar to what happened in solving linear equations by elimination, k over k is going to divide itself out. So 128 over 2 is just going to give me 64. And 8 to the p over 2 to the p, that's really 8 over 2 to the p power, which is just going to be 4 to the p power. And now again, technically you can do logarithms here, but it's easier in this case if you just say, all right, well, 4 to what power is going to give me 64, right? If I cube 4, in other words, if I make my power 3, I would get 64. So in this case, p equals 3. So there's my p. And now how can I get k? Just plug back into one of the two original equations that I had here, right? Just use the first one because it was easier, right? I have 2 equals k, which is still my unknown, times 2, but now I know that p is 3. So 2 to the third is 8. So this is 8k equals 2. So k is really going to equal 2/8, which in this case is 1/4. So there's my other unknown. And now I have my function, right? The power function again is f of x, so I'm going to call this f of x, and this is equal to k, which is 1/4, times x to the p, which is 3. And that would be my power function, right? So that's what you got to do there. You got to create a ratio, which is not obvious, really, right? It's not an obvious thing to do. So when you're stuck like that with a power function, or actually when you're trying to find an exponential function, which we'll do later in the second unit, you want to create a ratio because then things will cancel out, and then you'll be able to solve for one of the unknowns.